For the purposes of this class, we're going to talk about a calorimeter as a device that we can use to combine two or more substances that are at different temperatures so that we can monitor and control how the energy is exchanged between those substances as heat. Now, the reason we're able to sort of control what's going on here is because the calorimeter is effectively going to isolate the system inside it from whatever external environment that it's sitting in. So what that means then is that energy must be conserved. So what's inside the calorimeter, our system, won't be able to exchange any energy with the environment. Therefore, the total energy that it starts with isn't going to change. All it's going to be able to do is simply rearrange the total energy within inside the calorimeter until the system reaches thermal equilibrium. What that means, of course, is if the energy doesn't change, then when we add up these energy exchanges as heat, they always have to sum up to be zero. And so the key then becomes determining how many energy exchanges occur for the system to reach thermodynamic equilibrium. And so as a simple example, we can start with just combining ice and water. And so what you see here are four different plots. What can happen when we combine ice and water inside a calorimeter? The vertical axis on all these is showing the temperature. The horizontal axis on all these plots is showing the energy that's being exchanged as heat. And so the first option we've got here is if we have a small amount of ice that's not all that cold and a relatively large amount of water that's reasonably hot, what's going to end up happening is that the ice will start at some temperature below zero, its temperature will increase, it'll reach the melting point, it continues to take in energy as heat because the water is still warmer than the ice, they're not at the same temperature yet, so it's going to continue to take in energy as heat, and since it's at the melting point, the only thing it can do at this point is melt. Once all the ice is melted, again, if the water is still not at 0 degrees Celsius, they'll continue to exchange energy as heat. The ice now having melted into water, that ice will continue to increase its temperature as water until the system finally reaches a final temperature. So all the ice melts and can now reach a temperature above zero where all of it is water. Your entire system is water. If, on the other hand, the ice gets to 0 degrees Celsius and begins to melt, but before all of the ice melts, the water also reaches 0 degrees Celsius, then we know that our final temperature is going to be the melting temperature, right? It's going to be 0 degrees Celsius. And what we don't know then, how much of the ice eventually melted. Now these top two are situations where the ice reaches the melting point first. The water is still at a temperature above the melting point. Well, of course, if we start with a large amount of really cold ice and not much water, we can actually have the opposite occur. So the two on the bottom are showing situations where the water actually gets to the melting point first. And so as it gets to the melting point and continues to give up energy, it gives up energy to the ice as heat, so the ice's temperature continues to rise. But as the water now gives up energy, if it's already reached the melting point, what's going to happen, of course, is that the water is going to begin to freeze. How much energy it has to give up before the ice also reaches 0 degrees Celsius will determine whether only some of the water freezes, and again you're left with ice and water at a final temperature of 0 degrees Celsius, or whether all the water freezes, and so you have a situation where the water reaches 0 degrees Celsius, it all freezes, the ice has not yet reached the same temperature as the water continues to give up energy. As it does, its temperature begins to drop as ice now below the 0 point, and so you end up with the entire system now being ice at some final temperature that's below the melting point. So all of these are possible, and sort of what we know and don't know depends on sort of which of these things occur. So if all of the ice melts or all of the water freezes, we know the mass of the ice that melts in this case, we know the mass of the water that freezes in this case, it's all of the ice or water that we started with, and what we don't know is the final temperature. So here the final temperature will be above the melting point. Here the final temperature will be below the melting point, but we don't know what that final temperature is. On the other hand, if we have a situation where some of the ice melts or some of the water freezes, we know what the final temperature is because the only temperature where ice and water can coexist at atmospheric pressure happens to be at the melting point. So we know that the final temperature in these two cases is 0 degrees Celsius. What we don't know is how much of the ice has melted or how much of the water has frozen. We can look at these examples in a little bit more detail. So again, we're going to start with a situation where let's initially think about, well, how much energy does the water need to take in versus how much energy does the ice need to take in for both of our substances to reach 0 degrees Celsius. And here's a situation where clearly the amount of energy that the water needs to give up before reaching 0 degrees Celsius is much greater than the amount of energy that the ice needs to take in. So the next question we want to ask is, well, how much additional energy does the ice need to take in to all melt? And again, in this particular situation, we see that all of that energy for the ice to reach the melting point and then completely melt is still less than the total energy that the water needs to give up to reach the melting point. So what this means, of course, as our system starts exchanging energy inside our calorimeter, all of the ice is going to end up melting. So we'll start with when all the ice melts. Again, we'll sort of start, the water will give up energy, the ice will take in that energy, and it will take in the energy until it gets to 0 degrees Celsius. It'll continue to take in energy until it's completely melted, and then the ice now as water will continue to take in energy until it gets to the same temperature as the water, as it's been decreasing as it gives up energy until they reach a final temperature. So you'll notice that what there are here is there are actually 4 processes. So there are 4 energy exchanges that we need to keep track of within this situation. So we'll make a little schematic. So we'll start with the ice at its initial temperature over here on the left, so sort of the cool stuff on the left, the hot stuff, in this case the water, at its initial temperature on the right. And then to think about all the energy exchanges that have to happen, well, initially the ice has got to reach 0 degrees Celsius, then it has to melt. So the ice is converted to water still at the melting temperature. And then finally that ice is going to increase as water now to the final temperature above the melting point. The water, on the other hand, all it has to do is simply decrease in temperature down to the final temperature as it gives up energy. And so what you can see is we're going to start with an initial situation on the outside. So ice at its initial temperature, water at its initial temperature. And this is going to leave us with a final state where we have all of the ice has now been converted into water, all of the water that we started with, and all of that is at the same final temperature. So some temperature that's above the melting point. So this gives us 4 energy exchanges that we need to keep track of. And so if we think about what type of energy exchange each of these are, what sign they're going to have, because is it either taking in energy and so it will be positive, or giving up energy and will be negative? What mass do we need to include in each of these processes? And then what special value, based on if it's a specific heat process, what specific heat value do we need? If it's a latent heat process, what latent heat value do we need? And so for Q1, it's clear that the substance is the same. It's ice. It's changed its temperature from something below 0 up to the melting point. So this is a specific heat process. It's taking in energy, so it needs a positive sign. It's all of the ice that's got to take this in. And because at the moment it's changing its temperature as ice, we need the specific heat value for ice. For Q2, on the other hand, the ice is at the same temperature, it's just that it's changing phase, which means this must be a latent heat process. Again, it's got to take in the energy to do that, so we need a positive sign. The mass of the ice, all of it is going to melt, and again, we need the latent heat value for fusion because our ice is melting. Q3, well, now as water, it's going to change temperature from 0 degrees Celsius to some final temperature for our system. So again, this is a specific heat process. It's increasing in temperature, so it has to take in energy. Again, still this is all of the mass that started as ice, but now it's changing temperature as water, so we need the specific heat value for water at this point. Q4, of course, that's the water. It's changing its temperature from the initial temperature to the final temperature, so it's also a specific heat process. The water, however, is giving up its energy, so we need a negative sign. We're going to include all the mass of the water within this process, and again, because it's changing its temperature as water, we also need the specific heat value for water in Q4. So we can use this information to basically set up our equation, and so we know that if we add up all four of these energy exchanges, we're going to get 0. So we can calculate Q1. We said it was a specific heat process. Q2 was a latent heat process. Q3 and 4 were specific heat processes. And so just including all those values that we needed, the first three, Q1, Q2, and Q3, those involve the ice. Q4 involves the water. And so we've just chosen to go ahead and explicitly take care of the sign out front for each of these. For the specific heat processes, these temperature values, instead of being final minus initial, here they are final minus initial, but in all of these cases, they're actually hotter minus colder temperature, because we've gone ahead and taken care of the minus sign out front. Just being explicit about whether or not that particular energy exchange is taking in or giving up energy as heat. Well, what if we start with the same idea? We'll start with water at its initial temperature. We can calculate how much energy it has to give up to get to 0 degrees Celsius. We can start with the ice at some initial temperature below 0. We can see how much energy it needs to take in. And again, here's a situation where the ice doesn't need to take in nearly as much energy to reach 0 degrees Celsius as what the water needs to give up to reach that temperature. But if we also calculate out how much energy the ice needs to completely melt, it's actually greater than what the water needs to take in to reach 0 degrees Celsius. So in this case, what this tells us is that some of the ice will melt, but not all of it. Once everything gets to this point, the process is going to stop, because now the ice and water will all be at the same temperature. That final temperature is 0 degrees Celsius. So in this process, again, we're going to start the same way. We're going to get the ice to 0 degrees Celsius as the temperature drops for the water. Then the ice is going to melt. It's just in this case, it's not all of the ice that's melting. And then once it gets to this point, because now the ice and water are at 0 degrees Celsius, they're at the same temperature, we've reached thermal equilibrium, the process is going to stop. I can think about what are the processes that are involved here. And so I'll start the same way we did before, with my cold stuff over on the left, and think about what the ice has to go through, my hot stuff on the right, and think about what the water has to go through. And again, what I'll notice is the ice, again, it has to go from its initial temperature to the melting point. Some of it will melt, but that's the only processes that the ice have to go through. The water, on the other hand, is going to go from its initial temperature all the way down to 0. So again, I'm starting with my initial states on the outside. I can see what my final state is here in the middle. And so if I think about what's going on, is I only have 3 energy exchanges in this case. So unlike the last one where I had a 4th energy exchange, here I only have 3. And so again, I can sort of categorize what each of these exchanges are. Again, for Q1, it's a specific heat process because the temperature is changing. The ice is taking energy in. All the ice has to take that energy in, and because it's changing temperature as ice means I need the specific heat value for ice. Q2, of course, is where the ice melts, so that's a latent heat process. It has to take energy in, but the difference here is that this isn't all the ice necessarily. So here is just how much ends up melting depending on what the other parameters are within the problem. Again, because it's a latent heat value, I know I'm going to need a latent heat, and in this case I need the latent heat of fusion because I'm dealing with a transition from solid to liquid. Q3, again, that's the water changing its temperature, so it's a specific heat process. That water's giving up energy. All of the water is included in that process, and it's changing its temperature as water, so I need the specific heat value of water. So when I add together these 3 energy exchanges, I know they have to add up to be 0. And so again, we've set this up so we're being explicit out front about what the signs are for each of these processes. These two are positive, Q1 and Q2 are positive as the ice takes in energy. Q3 is negative, and so again I've got the hotter temperature minus the colder temperature to make that work out algebraically. So we said there were two other options. We can have a situation where the water actually gets to 0 degrees Celsius first. So the energy it needs to give up is less than the energy that the ice needs to take in to reach the melting point. So the second question becomes, well, how much energy would it take for all of that water to freeze? And again, I might have a situation where the energy required for all of the water to freeze is greater than what the ice needs to take in. So the energy that the water needs to give up to reach 0 degrees Celsius and all of it freeze is larger than what the ice needs to take in, which again tells me that some of the water is going to freeze, but not all of it. And again, I'm going to end up with a final temperature at 0 degrees Celsius. So when some of the water freezes, it's going to start the same way. It's just now the water gets to 0 degrees Celsius first. The ice, as it takes in energy, will warm up. It'll increase in temperature. It won't get to 0 degrees first this time. I can figure out how much additional energy it's going to take to get the ice to 0 degrees Celsius. All that energy's got to come from the water as it gives it up as it's sitting at the melting point. That water is going to begin to freeze, and then how much of that water freezes is just going to depend on how much additional energy the ice needs to get to 0 degrees Celsius. So that's going to be the final temperature of my system here. In my schematic, I can start with the cold stuff on the left, the hot stuff on the right, same as before. And again, I know that the ice, it only has a single process this time. The ice has got to go from its initial temperature to 0 degrees Celsius. The water, on the other hand, has to get to 0 degrees Celsius, and then some of it's got to freeze. So I start with my initial states on the outside, and my final state of the system's right here in the middle. And again, what I see here is I've got three processes, but unlike the case where some of the ice melted, here only one of the processes involves the ice, the other two involve the water. So again, categorizing these, I know that the ice is simply going to change its temperature. That's a specific heat process. It's going to take energy in, so it'll be positive. Q2, however, is where some of the water freezes, so that's latent heat. In freezing, it's got to give energy up, so I know the sign is negative. I don't know what that mass is. That may be one of the unknowns that I have to calculate out. I do know that I need the latent heat fusion to calculate what the latent heat for Q2 is. Q3, again, that's the water as it went from its initial temperature to 0 degrees Celsius, so that's a specific heat process. It was giving up energy, so it's got a minus sign. And again, all of the mass of the water is involved in Q3, and it's changing its temperature as water. So I can set up my equation where, again, I'm adding together three energy exchanges, Q1, Q2, and Q3. Those all have to sum up to be 0. And again, we're being intentional about what's going on with the signs. So we've set this up so that the positive is taken care of for Q1, and then Q2, there's the negative because it's giving up energy, and Q3, there's the negative, and again, we've got hotter temperature minus colder temperature to make that work out algebraically. Our last option, of course, is that we can have a situation where all the energy given up by the water to get to 0 plus all the energy it would need to give up to entirely freeze is still less than the energy that the ice needs to take in to reach 0 degrees Celsius. Which of course means all the water is going to freeze, and so I'll end up with my entire system at some temperature below the melting point. So when we set this up, the water is going to get to 0 degrees first as it gives up energy. It's going to completely freeze, but the ice still hasn't reached 0 degrees Celsius yet. So what's going to happen is the water continues to give up energy now that it's ice at a warmer temperature. It will end up cooling to some temperature below 0 degrees Celsius. Once it reaches the same temperature as the ice, now we've reached thermal equilibrium at our final temperature. So again, setting up our schematic, what we have is one step for the ice as it goes from its initial to final temperature. But there are three steps for the water. It has to get to 0 degrees Celsius, all of the water has to freeze, and then all of the water as ice will cool off to whatever the final temperature of the system is. Again, our initial states start on the outside, and we're left with our final state in the middle. We have 4 steps here because there's now 3 processes that the water has to go through. So we can characterize what these processes are. Q1, of course, is the ice changing temperature, so it's a specific heat process where the ice is taking in energy. Q2 is also a specific heat process. It's where the ice has gone from 0 degrees Celsius to the final temperature, so it's giving up energy. All of the water is included in that, but it's changing temperature as ice now, so I have to make sure that I've got the right specific heat value. Again, before that, it had to undergo a latent heat process where all of the water froze, and then before that, it had to start with a specific heat process where it went from its initial temperature to 0 degrees Celsius. Again, in this case, it was still water as it underwent this temperature change, so I need the specific heat of water. So there are going to be 4 steps that I need to include in my equation. There they all are. And so I've got the mass of the ice, the specific heat of the ice times the temperature change of the ice, and then I've got minus each of those Q terms for the 3 processes that the water also undergoes.